Good morning. We're about a minute early here, but we can get started and see who trickles in. My name's Eric Evenchick. Today I'll be giving a talk called RustZone, Writing Trusted Applications in Rust. We'll be going through sort of how TrustZone works on ARM and how it gets used in the real world, where it breaks down, and then look at sort of a proof of concept of how we can use the Rust programming language to write trusted applications for TrustZone. So a little bit about me. My real job is I'm a principal research consultant at Atreides Partners. We do penetration testing and other security services, risk advisory, things like that. I'm based up in Canada, in Toronto area. We have folks in the US and Canada, and we're just sort of all over remote. My boss likes to say we're post-geography, so we just have folks wherever. And I also build some random open source hardware with this company I have called Linklayer Labs. We just build things and put them on the internet, and some CAN bus tools. Actually a hardware implant, if you saw the hardware implant talk, and some things like that. But today we're talking about not hardware, really. We're talking about, ARM. And a little outline of what we're going to do, what we're going to cover. So we'll start off just by talking about trust execution environments in general, and what they are, where they're used, some examples of them. And then I'll go through TrustZone. And TrustZone's a word that gets thrown around a lot, but we'll show kind of how it actually works and how it gets used in the real world. Then talk about some of the issues with the code that's running in these things. Introduce Rust a little bit, talk about Rust. And then we'll put it all together, talk about how you can use them to make a trusted application in Rust. Demo a pretty basic one that we can show sort of on a slide, and take any questions you folks have. So, starting with just trusted execution environments, a topic that's actually made the news quite a bit due to some of the Intel and AMD problems with trusted execution environments. But what are they? So the general definition would be an isolated environment within a processor where you're going to do some sort of secure operations. So this is a place where you're going to get some segmentation of your code and your data so that you can do things and not be observed by other parts of the system. In some cases, it will also segment hardware access. So you'll be able to access certain maybe I/O pins, pieces of memory, whatever it is, that can't be accessed otherwise unless you're in this trusted execution world. So it allows you to provide that separation and draw trust boundaries around your application. And this is done with a combination of some hardware features that are actually in the chips that your stuff's running on, and a bunch of software that makes it all work. So when you look at today, what's out there, what people are using, some examples on the hardware side, AMD has their PSP, Platform Security Processor. This made the news a lot because it has a lot of issues that have come up in the last year. One interesting issue with some of this trusted stuff is when it breaks, it's really bad because all of the high security things that you really care about are living in this world. And when they fall apart, it's really critical. In the case of PSP and some of the Intel stuff, it provides very privileged access to the processor. So if you manage to get code execution inside of there, you're bypassing a lot of the security features of the chip. Intel has their TXT, Trusted Execution Technology, and also software guard extensions that they use. You might have seen some of that stuff marketed. And ARM, of course, has TrustZone, which is one of the more well-known, more talked about systems. And the reason for that is it's very common. If you have an Android phone that's recently modern, it is running TrustZone, and it is running a TrustZone Trustlet, which is an application in TrustZone. Every time you log in, you enter your PIN code, it's going off to the trusted LAN, doing some verification, and coming back. On the software side, there's a few different things depending on what you're using. So AMD and Intel have their own magic software that runs on there. It's all proprietary. They won't show it to you. And that's also been a bit of an issue. But on the ARM side, we have a range of trusted operating systems. Trustonic Kinibi is one of the ones used by Samsung now. Qualcomm has QC. This is used on most of the phones, not all, the phones that use Qualcomm chipsets. Google also now, it's not on this slide, but Google has their own open source trusted OS called TrustZone, and that's used also on some Qualcomm chipsets. It's used in the Pixel 3. And then you have TEE, which is the one we'll talk about the most today, mostly because a lot of this stuff is not open source. It's proprietary. They won't show you what's inside. OpTEE is an open source implementation of a trusted operating system. So you can, actually, one, you can build it yourself. And two, you can talk about it at a conference because you didn't have to sign a bunch of NDAs to get access to it, unlike QC. So that's just the reality of some of these things. While OpTEE isn't actually that common in practice, you don't see it in too many devices. You don't see it in mobile phones. It is something that you can talk about. If you want access to the source for something like QC, you're definitely getting into a lot of NDAs. And Qualcomm has a lot more lawyers than I do. So the use cases of this stuff, authentication is one I talked about. Android has the gatekeeper functionality, and this is actually shown on the side here, on the right side. So you have this lock setting service. It's going to talk through Binder, which is the user LAN IP inter-process communications that's used by Android. And it talks to the gatekeeper service, which is a little server that's sort of running there. That ends up talking to Gatekeeper D. There's a lot of layers to this sandwich. It goes down through Gatekeeper D, talks to the Gatekeeper hardware abstraction layer, which talks to, finally, the Gatekeeper hardware abstraction module. And then that has a bridge that goes into the trusted execution environment where there's a Gatekeeper trusted application running. So you enter your PIN number. It makes it through all this stuff, eventually gets sent over to the trusted world where the valid number is stored. And the comparison happens over there, and if it's correct, it will send back, you're good. This way, if someone compromises your system, they can't get that type of data because it's located in a trusted environment. So that's one example. Financial applications make some use of this, and some systems will expose the ability to access that. One example of this that gets used is some of the Bitcoin wallets, which vary wildly in their implementations. But some of those will use TrustZone to actually store the key material. So you'll have a Bitcoin wallet that's got USB or it's got a screen on it, whatever type it is. And it will make signing requests into the trusted world where the key material is stored, and it will get out a signed transaction. And so that way, that actual private data of your private key for your wallet is always sitting in this trusted environment. It never leaves the trusted environment, and it's just being used to do signing operations. Secure Boot's another place this comes in because you can have this separate world that's doing validation of things, and even if your kernel is malicious, it can actually validate that separately, and in some cases do stuff like reset the system immediately if it doesn't like what's happening. It's also used for DRM, which is an interesting application. WideVine is one of the main applications for one of the ones you'll see on Android. It's a product for Android. We'll talk about that in detail a bit later. So the main thing here is you're getting this extra layer of protection from the host OS and the normal user LAN. So you have user LAN, you have the kernel space. That's all separate. It's talking over a bridge to this other trusted world. And it is sometimes used to protect the system from the user, which is a nice way of saying stopping you from doing things that you might want to do to your device. For example, there are mobile carriers that have applications that run in TrustZone that are used to do SIM card locking to prevent you from unlocking the phone and using any SIM card with it. At least in the US, it might be different here. But that is one application where you as a user might not like this whole TrustZone thing. But let's talk about TrustZone, how it works, what it actually is in practice. This is sort of the ARM marketing speak of it, the trusted and non-trusted world. And it's the ARM trusted execution environment, and it has the normal, they call it the normal world, and the secure world, which is a bit of a misnomer. But the normal world is going to run typically your rich OS, so your Android, your Linux, your QNX, whatever normal OS your normal applications run on. The secure world is going to be some limited operating system, like OpTEE in this case, that is only going to be able to do certain things and will also have trusted applications, which are things like the gatekeeper daemon, other examples on Android, WideVine, things like that. The processor has the ability to switch between these two worlds, and it can also use this to restrict access to different peripherals. So really a useful example, this is taken from the Gnode documentation, but this sort of shows how the flipping works and what actually happens. So you got your normal world on the left, and the big thing to notice here is that there's a secure configuration register with the NS bit. I kid you not, NS stands for not secure. So when not secure is 1, your system isn't secure. You're in the normal world, and you're operating on the peripherals as they're configured for the normal world. So in this case, we have our CPU core, we have some instruction cache and data cache, and you see red bands of regions that are enabled in the normal world. We have a certain amount of RAM that's enabled, we have some L2 cache that's enabled, and we have a set of peripherals that are enabled. So we have Ethernet, USB, MMC, all the ones that aren't grayed out. So we're going to be living in this world most of the time until the processor decides to unset the not secure bit, which brings you over to secure land. And what ends up happening here is we still have a CPU that is still running, but we have different instruction cache and data cache. We have a different bank of RAM. We have a different bank of L2 cache. And really critically, we have different peripherals. So things like the GPIO pins can only be controlled from that secure world. So let's say you have, I don't know, some industrial robot that's got some actuator that's really dangerous, and it's controlled by a single GPIO pin. Hopefully it's not, but it's controlled by this one pin, and you only want that to be able to be done in certain conditions. You could have it so it's only possible to set that bit whenever you're in secure world. Also, critically, there's a security controller at the very bottom, and that's only enabled in the secure world. Typically, those security controllers will have things like crypto acceleration functions. Sometimes they'll have key storage. Modern ones all will have key storage and onboard key generation. So the ability to do things like signing of arbitrary data will be available to you only in the secure world, so that if somebody gets root on your Linux system, they still can't actually make requests to it. So this sounds really nice. We have this nice segmentation. We have these two worlds. They're separate, but kind of equal. A lot of this will depend on how you configure the processor. And a really important note is if you screw up configuring the secure world and the normal world, you can end up on certain processors just completely negating the whole point of TrustZone. If you want, on some processors, you can actually have memory that's shared between the two, and you can have as much memory as you want shared between the two. So if you configure it wrong, you may end up just totally defeating the purpose of it. And that has come up in some applications, that it's just been configured incorrectly, and it just totally breaks the whole purpose. So on that note, what are some problems that we run into with these trucks execution environments? And, well, the first one is really the sort of theme for this talk, which is there's a lot of protections that aren't there. So address-based layout randomization is starting to become more common, but is still quite rare. There's also this problem that these limited OSs, because they want more memory for the main system, they have a very limited memory range. So there are attacks on some of these trust applications where even if there is layout randomization, there's so little memory that you can just try it a whole bunch and eventually it will land where you want it to. That's happened for a few different, we've seen it a few times. So there's no stack canaries or guard pages on a lot of these, which would be nice. Some of the more modern OSs are starting to actually add that, but also some people don't compile it with those flags enabled. The secure world will actually, in most cases, have fewer protections than the normal world, which is weird, because this is your secure, really locked down system. Why doesn't it have ASLR when your Android system definitely does? Why doesn't it have stack canary guard pages, all those types of things, when we've been using those for years in the normal world, but the secure world just really hasn't caught up. And one of the biggest things is we don't have high-level language support. So there's no Java. You're not writing this stuff in Python or anything like that. You're writing it all in C or ARM assembly. And that brings up all the usual problems of writing C. So writing good C is really hard, maybe impossible. If given a certain number of lines of code, you will probably not be able to write secure C. It is unfortunate. So you have all the typical stuff that we've been seeing for years. There's the common memory problems, the buffer overflows, use after free, all that sort of stuff. You have the typing issues. So there's lots of places where when you interact with these secure OSs, you're providing void pointers to things and length values, and those are really easy to mess up. The compiler, of course, gives you very limited help. If you're smart, you'll turn on things like WAL and get warnings as errors and things like that. But people don't necessarily do that. And when developers run into these types of problems and their stuff doesn't compile, it's sometimes, if you don't stop them, it's sometimes more tempting to disable the error than it is to actually fix it. And C will happily let you disable whatever errors you would like. And programmers do silly things. This is no surprise to anyone in security. They do their mem copies and their stir copies and all those other functions that we're not supposed to use anymore. This is a nice poster from one of the folks at Project Zero, Natalie. Basically, she took this, fellow Canadian, took this campaign that Canada had a while ago about, being safe about different things, and made them about being safe about calling different functions. This one is, all my friends are using strcopy, but I'm not because I understand how dangerous it is. They say I could protect myself, but I know that only avoiding strcopy is 100% effective. And that's true. If you're calling this type of stuff and you have a bunch of developers, eventually someone's probably going to end up with a buffer overflow. It's just the world we live in when it comes to developing C. So let's talk about examples of how people have screwed it up. WideVine is a DRM application that probably a lot of the phones in this room have. Again, if you have an Android device, it's likely running it. And it's used so protected content can be delivered and decrypted by this application. The keys live inside of TrustZone, so you can't get the decryption keys for the content. Kind of an overview explanation, but that's more or less what it does. So there was an undocumented command, actually a whole set of undocumented diagnostic commands that WideVine had. Somebody grabbed the binary for this, which is actually quite easy. Typically, these are not encrypted applications, and they're actually available from the file system from the normal world. So you can, if you have root on your phone, you can go into the right block device and just dump it, and you'll end up with all the TrustZone applications. So they went through this, they found some command dispatcher and found out that there was a command that ended up, it was being used for diagnostics, wasn't being used anymore, but it ended up having a buffer overflow inside of it. You could provide it with something way out of range, and it would happily end up smashing a buffer. And the end result was that these folks got code execution. It's the Bits Please blog, which has tons of great information on breaking TrustZone. But they got arbitrary code execution in the secure world. This is highly problematic because all those protections against different types of peripherals and memory, they kind of go away once you have code execution in that world. There are still some protections that the OS has, but you kind of have gotten through the gates. So in this case, they're able to run code in there and undermine the whole purpose of TrustZone because of a DRM application that you probably didn't want on your phone anyway. So that's life. There's more info about this on that Bits Please blog. If you're interested in this sort of stuff, I highly recommend that blog in general. They have a ton of great examples of breaking different TrustZone stuff. Another example that came up, another real world one, was Samsung. So they had this one-time password generation thing that was part of Samsung's Knox security package. And this was implemented, the whole Knox thing was implemented as I believe actually a couple different trusted applications running in TrustZone, and then services on the Android side to call into them. So they had one of these that generated one-time passwords, and what was very interesting about this one is the WideVine one, to actually pull that off, you would need to have root on the phone. But because Samsung wanted to provide access for any user to be able to generate these one-time passwords, any user was able to make this call. So now you go from needing privileges to basically just needing to be on the phone. So any application could call over Binder, the service, and then make the request. So that's much worse. And what ended up happening, again, another silly buffer overflow thing, you could provide it a value for the one-time password that was too long, and it would end up causing a buffer overflow, and you could go from there to getting code execution in TrustZone. So these things happen. These are two real-world examples that are public. There's probably many. I know there are a few more that are not, and I'm sure that there's many, many that I don't know about. It's a real problem when you're writing C on your most secure platform. So why do we want to talk about Rust? Well, yeah, if people are screwing up writing this code, maybe we should look at languages that give us a little bit more protection. So has anyone here written any Rust in their life? A few folks? It's a bit new. It's been in development since 2010, so it's new for a programming language. I mean, I'm always amazed, like, how old C is, right? Like, that goes back to the PDP 11 before that, and I mean, the standard that most people are still using is either 89 or 99. A lot of stuff is still 89 on embedded systems. So 2010 is like, yesterday in terms of the age of systems languages. And one of the big things about Rust is it is a systems programming language. It's designed for doing low-level stuff. And this is quite nice for us because it's going to not need access to a whole bunch of things that most programming languages will want in order to run. So, for example, the reason it works with embedded, it does not need libc, which is a big limitation when you're dealing with, most programming languages. It compiles down to actual system bytecode, so we don't need to run a VM, we don't need to run an interpreter, anything like that. It has no garbage collection or runtime. So this is one issue with something like Go. Go will compile down to a binary, but it still has this runtime, and the runtime depends on a lot of OS features. So you can't really run it without the operating system. And then lastly, it's going to allow raw memory access. And this is something that we want to avoid as much as possible, but we need. The reason being, if you're dealing with these embedded systems, these microprocessors, you want to set a GPIO pin to 1. The way you do it is there's some memory address that you write to, and you write a bit to the right bit field, and that sets the pin high. And that's just how it works. So you can't really abstract that away when you're dealing with this stuff at a very low level. It's just not really possible. So you do need access to the raw memory just to set stuff up and set values. So why is Rust maybe good for this situation? Well, it has a ton of compile time checks. So Rust has this whole model of memory ownership and borrowing, which is, you could have a whole talk on how that works, and there are actual whole talks on how that works. But one way to think of it is that Rust is kind of taking care of watching what you're doing with memory and making sure that you're not doing anything that could result in common errors. So whenever you pass a pointer to something, if it's not marked as mutable, it will not let it be mutated. And if it is marked as mutable, after it's returned, you can't actually access that anymore unless you've specifically said that you want to. There's a bunch of different implementations that make this work, but in general, it's watching your memory and it's doing it at compile time. If you write code that has memory problems, it just won't compile. And there's no -- disable memory protection flag that you can enable that will just let it build. It'll fail. It'll give you nice errors for the most part. Rust has been working a lot on making their errors better because they were really bad originally. And it will tell you, hey, on this line, this is not mutable and it should be, or you need to make this not mutable because of what you're doing, things like that. It is generally good at finding bugs at compile time instead of runtime. And part of this is the memory stuff, just the general memory protections. But another one is things like the match. So if you've ever written C, imagine a few people here have, you've probably written a switch case statement once in your life, and you've probably missed a break statement once in your life. Stuff like that doesn't happen in Rust. Rust has match instead of a switch case. Every single case has to be in a block that terminates, and you must match every possible value. So you don't have default. Well, you can have a default, but you don't have this generic pass-through where if it didn't match anything, it keeps executing. So silly logic bugs that come out of those types of errors that get made all the time just go away because it's harder to make those types of errors. And this is just sort of some of the insight that you get when you start writing a programming language 40 or 50 years after C was developed, right? The tools are pretty good and getting better. Like I said, the error handling has gotten a lot better. There is a tool called Cargo that you use to set up a package and install dependencies and build your project. So unlike with C, where you got to do a lot of hoops to get like a tool chain set up, and if you're relying on some dependency, you probably have to go out to the internet and download the source for it and put it in figure out how to build it, build some library, and so on. With Rust, it's kind of done for you. There's some repository of all these packages. It's called crates, and you can use the cargo application to pull down different crates, much like Python's pip or things like that. Of course, there are a lot of security issues with those types of systems, but it is available to you. And it has a really nice C foreign function interface. And this is really critical for doing any type of work like this, and we'll talk about it in a bit of detail. So in general, we're going to need the ability to both call C from Rust and this one's a little harder, call Rust from C. And the way that we do this is with CFFI, foreign function interface. And whenever you're writing Rust, we have all these memory protections in place. There is one way to get around them, and it's called unsafe. It's actually the same keyword you see in C#. And what it will do is you can say, this code is unsafe. It's going to access raw memory. It's going to call a function that accesses raw memory, something like that. And you'll use that keyword. So you do need unsafe blocks for dereferencing raw pointers, so if you want to access raw memory. Calling an unsafe function or method, which you could make a Rust function as unsafe, or if you're calling a C function, it's assumed to be unsafe because C doesn't have the safety, so it's unsafe always. Accessing or modifying a static mutable variable, which is something Rust really doesn't want you to do, is use static variables. And lastly, implementing an unsafe trait. So Rust has this trait system that's used to sort of describe different functions that an object can do. And you can have one that is completely unsafe and implement that trait. So it's just a language feature to stop you from having to write unsafe a bunch. But your goal is always going to be to limit this unsafe code. And in fact, if you compile something in Rust and you have an unsafe block, if any statements in that block are not actually unsafe, it will warn you. And it will say like, hey, this isn't unsafe. I don't know why you are calling it as unsafe. So you can take it out of your unsafe block. So it gives you a nice picture of what code you're running is memory safe and memory unsafe. Unfortunately, again, when we're dealing with these embedded systems and we need to access raw memory, there's no way around this today. It's how computers work. Unfortunately, we're stuck with it. In terms of learning Rust, this is not a whole talk on Rust. So what are some resources you might like? The Rust book is sort of the Bible, I'd say, and it's available online in full. It works you all the way from Hello World through to basically all the language features. Probably best for people who have already done a bit of programming. Like, it's probably not the greatest idea to say, oh, I'm totally new to programming, let's pick up Rust. But the book's pretty good. You give it a try. The paper version, this says soon. The paper version is actually now. No Starch has it. You can buy it in Dead Trees with the little crab on the cover. Rust by Example is a really great website where you can go through they have something for basically every language feature, and they'll show you an example and explain how it works. It also has a run sandbox thing where you can modify it and hit play, and it will run the code in your browser. So it's a nice way to play around with it. I always end up there when it's like, oh yeah, how do you actually use this particular feature? Oh well, just Rust by Example. It's got a page on it. And then there's Julia Evans's blog, and she has a great blog on lots of stuff. But she did a lot of work on sort of doing low-level stuff with Rust, and a lot of it is illustrated and quite entertaining, actually. So I generally recommend her blog for all sorts of topics, but it has a lot of Rust-specific content as well. So if you want to learn Rust, that's some of the resources. You can go out and do it. So I guess the last part here, we talked about TrustZone, we talked about Rust, and now we got to put them all together. And there's sort of a playbook to this that I came up with. There's a few steps. So the first one is we need a trusted OS. And we're a bit limited, right? Because if I used QC, well, first off, Qualcomm is not going to give me access to QC. But even if they did, then I'd be stuck up here with like a redacted slide. So we're going to use opt-TEE. It's free. It's open source. It's pretty well documented, and it also works with QEMU. So I don't have to have like a BeagleBone Black up here plugged into a projector to make it work, which is nice. You can also run it at home without buying any hardware, which is great. Another option that's a bit newer, the documentation for it was sketchy at the time, but now it's a lot better, is Google's TrustZone. You can go out and look at that. Google provides that all open source. And it's probably, going forward, a better thing to look at, just because it's going to be on a lot of Android phones. And TEE, they have a website, it's part of Linero, sort of, so they provide all the source and everything. So we have our OS, and we can run our trusted OS, and also we end up with a normal world OS, which is just Linux. So the next step here is to generate Rust bindings. TEE exposes this pretty big API that lets you do everything from println to HMAX and signing and all the crypto functions. So we need bindings to that, and it's all C headers. This would be hugely painful if we had to do it manually, so there is a very magical tool called bindgen for Rust. The way that this thing works, you point it at a C header file, and it takes the function prototypes from C, like this tmachinit function. The top one is a C normal, C function prototype with C types, and it will convert it into a Rust function. It looks pretty similar. There's a little bit more verbose. You'll notice there's an extern C block around it. That's telling us that it is an external function that is written in C. And we'll also make the FFI calls work. Rust does stuff like mangle function names. And whenever you're doing extern C, it knows not to mangle things, because otherwise C won't be able to find it. So it does this all automatically. That doesn't look that hard, but whenever you're talking about thousands of functions and enums and typedefs and all that stuff, yeah, this tool's really nice. And it works quite well. I've had no real issues with it on a variety of different C libraries. So once we have our bindings and our OS in place, we need to write a Rust library. And this is sort of backwards, because you figure we'd write an application, but we're going to write a library. The reason for this is the calling convention for TEE, it's not your normal, like we have an elf and we're going to call main. Instead, it looks for these 5 functions and it calls them at specific times. So this Rust library will end up getting loaded into the TEE OS, and it's actually given a GUID. And what will end up happening is whenever you call into that from the normal world, it'll make a request to first, it's the entry point is the first thing that it hits to actually create or set up the trusted application. And then every time you access it, it's going to open a session. So it'll call the open session entry point. You can allocate stuff there or whatever. Then it will invoke however many commands it would like to. And these are where you would implement your handlers to actually sign stuff or validate stuff, whatever you want to do. It'll call the TA invoke command entry point. It can call it once, it can call it multiple times, and then it can close the session, can open another session, keep going, and whenever it's completely done with the application, it can destroy it with the destroy entry point. So it's just 5 functions. We need to expose those. We need to expose them in a way that they can be seen by TEE, and that's about it. So there's some magic wrapper code that I've written, and all the source for this is available at this end. I'll give you the GitHub link. But there's a bit of wrapper magic that maps all the TEE stuff to the Rust stuff. But what you end up with is the ability to just write a Rust function like this. And we'll walk through this in a bit of detail. So this is the invoke command entry point for a very simple example, because I wanted it to fit on a slide. And this also happens to be the TEE hello world example. So it's, it actually works with their normal world application, which is kind of nice. So just like in C, we got our parameters here. It gets past a session context. This is one of those cases where we have a void type because we're dealing with C. But we have a command ID, which is going to be some number. Param types, which are going to be the types that end up mapped to the parameter array, and then an array of parameters. Now, this is a very simple function that just increments and decrements values. But the first parameter that's passed has a value that we want to increment or decrement. So now the arrow here is telling us our return type, and that's an TEE T result. That's a enum that was actually defined in the API, and then bindgen made us this type. So we can just do TEE : and get access to the whole API. The next line here is a Rust macro. The reason you know it's a Rust macro is because of the exclamation point. And this is a macro that's going to end up doing a little bit of massaging and then calling one of the functions in the API to do printf, basically. It was just kind of annoying to print a string. You had to do some buffer conversion things, and I wanted it to be easy, so I wrote a macro. One benefit of Rust that I didn't mention over C is it has a macro system that won't make you go insane. It has a lot of nice macro features. If you've written C macros and done like do while zeros and things like that, you probably, you'd like Rust's. So this is just printing. Yeah, we're in the invoke command entry point. And then we're doing a match statement. So this is like a switch case. We're matching on the command ID value. And this is sort of a functional programming kind of thing, because we're matching 0. This is where we need to call an unsafe, because we're modifying essentially raw memory here. And we're taking param 0.value.a and incrementing it by 1. So in this case, command value 0 is increment. And then it will print incremented value, just so we know. And then we have command value 1, which is also just a different match value, and it's going to do the same thing except decrement the value and print decremented value. And then we have this underscore. If you do not include this underscore match, this will not compile. It'll say you did not match all the possible values. And this is really nice because I know I've written a lot of dumb code and done things like, oh, I don't need to return an error here. I'll go back later and put in the default case. That's fine. And this won't let you do that. You have to write the case to match everything. And in this case, opt defines this error bad parameters, which is the perfect return type for that. So if I see something that's not 1 or 0, I'm just going to return error bad parameters. Otherwise, we finish the match and return opt success. So again, probably the most complicated demo I can fit on one slide, but it does something. And the last step is to get this whole thing built. And if you've dealt with the joy of linkers, this is a little bit of a challenge to get working the first time, and then once it works, you never want to touch it again. But what we end up with is a compiled Rust library, and then there's some other pieces to this. So there's a trusted application header, TA header, that is provided, it's built by the opt API. And what that is it has the GUID of the application, some other information about the application. That part is written in C because it defines some magic constants, and you just let it do it, and gets compiled down to an object. So the other thing is this libut, libmpa, and libutil. This is the actual dynamic libraries for we're going to be calling into. And if the linker doesn't get those, it'll say, oh, I don't see this symbol, I won't compile. So we need to take all three of those things and toss them into the linker. So once we have that, we have symbols, all the symbols that we need. We need a linker script. opt provides one of these that fortunately works, just works with it. So that part's pretty easy. And we toss that into the linker. We end up getting an elf out, just like any other elf. The only little caveat here is my system is x86-64. Most of a TrustZone is going to be ARM because, all of it's going to be ARM because it's ARM's copyright. So we're doing cross-compiling here. Rust has a very nice cross-compiling system. You can use Rust up to install the various targets. You need a cross-compiling GCC to build the header and the libraries. You need a cross-compiling linker to do the linking. When we have all that done, we end up with an ARM elf for the trusted application. The last step is to call this little function little script that's provided by opt to do the signature. So it will take that binary and sign it, and that way, whenever we actually try to run it, it will check the signature and make sure it's valid. opt will only run signed code. So this is a pretty nice protection. And what that ends up doing is just tossing a signature on the thing, and it gives us a signed trusted application. And finally, we have something that we can actually run. And we'll do a little demo. Now, I apologize. QEMU, bit of a pain in terms of font size. Oh, that's lovely. Internal error. We'll just hope that that wasn't bad. Bit of a pain in terms of font size and in terms of lighting. I hope this is somewhat visible. I'm not sure if the lights can can go down to wash out less. But the way this ends up working here, when you build this, it will build you a QEMU image. So it builds you both a build root image for Linux, and it builds you the trusted world. So we're sitting over here at QEMU, and we're going to hit C to start it. Lots of junk flies by just as it boots. Top is our normal Linux system that was U-boot, and now the Linux kernel's booting. The bottom, we're looking at the secure world, which is just printing out some debug messages. If you were on real hardware, this would be set up as probably 2 serial terminals. Interesting note, if you happen to be pen testing any of these systems, sometimes the trusted world's debug serial terminal is left enabled and can provide all sorts of juicy info. Yeah, so we're going to log in with the super secure login of root and no password. And now we're sitting at your normal like Linux, like, hey, this is ls/. Yeah, it's a Linux system. It was built by buildroot. It's a 32-bit ARM system. So what optee provides as their examples is a bunch of normal world applications. So you're going to call a normal world application, and then it's going to end up doing the actual IPC that happens over to the trusted world. It'll do some stuff, send back the result. Their hello world was a great example because it was that nice simple example. So we call hello world, or we run hello world. And what we see happen is a value gets incremented. Really simple. But what happened there, it was actually loaded up. You can see the GUID starting with 8 AAF. It's real tiny. But it called it, and it was printing the Rust TA create entry point, all the things that happened. So it create entry point, it did a open session, it didn't invoke command, it printed incremented value from Rust, then it closes the session, close session entry point, and then it actually destroys the application. It doesn't keep it open, so it does destroy entry point. And then it's done. So that's what it ends up looking like with both the worlds interacting with each other and how stuff gets passed together. In practice, when you called that application, that not secure bit ended up getting set to 0, which passed execution over to the secure world, which invoked the thing, got the parameter, incremented it, printed out some stuff, and then threw the value back into the normal world. And the bit got switched back when that happened. So just quick demo to show you it actually works. But the code's all provided if you want to download it and try it yourself or look at it in more detail. But a few little conclusions, some takeaways maybe, is, well, this trusted execution environment thing, it's useful, but it's not magic. You have all the usual problems, right? People can misconfigure it. People can write vulnerable code. All the normal things that could happen anywhere else, except there's actually some things that are against you, right? You're writing C. You have bare metal access to all this stuff. Like, there are some reasons that it makes it even easier to screw up. So if you come across these, don't think that, oh, well, it's a trust execution environment. There's nothing that can be done. It's the same as any other application at the end of the day. Rust is a potential replacement for C in a lot of these applications. And what I mean by that is it can do a lot of these things. The reason being it doesn't have any dependencies. It needs like memcopy. And it also has some of these benefits, things like some more sane semantics around macros and match and things like that, the memory protection, so on and so forth. So there's some reasons that you might want to use it. Probably the biggest disadvantage is that very few people in the world right now know how to write Rust compared to C. You're unlikely to just find a Rust developer that is going to write this stuff. As far as I can tell, no one else has tried to write a TrustZone application in Rust. So there's not many people that are going to do that. That's a problem. Also, some of the stuff is going to be more work and more verbose because of the memory protection, things like that. And then I guess the last is sort of like a question, which is, should you do this? Which is always a good thing to ask when people give talks about, ooh, I have this nice thing in proof of concept. You can always be like, yeah, but is it really a good idea? And I think maybe not yet. The ideal thing here would be if somebody wrote an operating system for TrustZone that was sort of more Rust-focused and had better support for it. I'm stuck with not having the Rust standard library, for instance, because it has a lot of dependencies, things like that. But it is something you can start looking at if you have places anywhere, not necessarily just TrustZone, where you're saying, well, we're using C for this because we need to for one or two things, maybe it's time to start saying, well, could Rust replace it, and is that a good idea? And in some cases, I think the answer is yes, but it'll depend. Anyway, that's what I have for you today. You can send me emails or find me on Twitters. All the code and slides are on GitHub there. And I think we have about 5 minutes if you folks would like to ask questions. But thank you very much for coming out. Thanks to the Black Hat folks for having me and people who put this on. It's always fun to get up in front of folks and talk about what you're working on. So thanks. I don't know how we're doing questions, but oh, there's a microphone.
Hi.
Hi.
Thank you for the talk.
Thanks.
It was very nice. I have a question about you were saying that people, the trust zones, they will be more secure if they go, for example, to Rust, right? So what about, for example, like bugs that they are not memory corruptions, like a arbitrary write, like a write zero vulnerability where you can basically knob all the things. They could be possible in Rust as well.
Oh yeah.
So
it's not, none of this stuff is a panacea, right? Like none of it's going to solve all your problems. That's anyone who's selling you a security product that solves all your problems is lying.
It's only one bug, and it doesn't matter if it's C or Rust, and you are.
Yeah,
it's gone. It's game over.
And that's actually a problem with trusted execution environments. One thing about this talk is if you're someone who tests these for a living, it maybe gives you some ideas. But again, if you run into these, all those bug classes, totally valid. The only difference is you have some weird IPC mechanism to talk between the two worlds, right? And you can't do certain things. But look at it as another level of, you got user, you got root, and it's just another level of privilege. If you wrote a Rust application that was vulnerable, that was running as root, and that was setuid root, you'd have the same problem. But there's certain bug classes that will help you prevent against, and certain reasons that might help you. So, again, none of it's a magic bullet. I wish there was a language that stopped all security problems, but it's unfortunately not the case.
Do you think that the industry will move someday to, for example, Rust?
I think pieces of it might start doing that. So folks that are doing some embedded things and sort of higher level embedded. So, you have the really low level, you're writing code for like an 8-bit microcontroller and whatever ASM it uses, like that stuff's, no. You go up the stack and you have things where you're running a full Linux system and you don't need to access hardware directly. That you can also use things like Go or Python or whatever, where you don't get all the benefits, but you get a lot of them. The stuff that sits in the middle, where you have something that's embedded but needs hardware access, is one place where I can see people who really care about security starting to look towards it. And also places where you need those types of, I guess, security benefits, but also real time. That's another benefit compared to something like Go, is because there's no garbage collection, you can actually do hard real time stuff. And you can't do, other than C and assembly, doing hard real time it's not easy. So that's, another reason that might help you out. Thanks. Anyone else? If not, I'll let you go 2 minutes early for lunch. I'll be around here if you want to ask me a question privately or in one-on-one. But thanks again, and have a good day. Enjoy the rest of the conference.